Hi, everybody. Now that we have the basic idea of what we mean by the range of a transformation and the kernel of a transformation, you might want to know, what do we know about these sets of vectors? The first thing you find out is that they're actually subspaces for their corresponding vector spaces, which means they have dimensions. So we can define their dimensions. We'll call them the rank and the nullity. And that's very similar to something we've heard before, right? So we should eventually, in the end, get what's called the rank nullity theorem. So first off, the kernel and the range are definitely subspaces. So if you have a linear transformation going from vector space V to vector space W, then the kernel of T is a subspace of V, and the range of T is a subspace of W. You can then, since they are subspaces, they have dimensions. So you can define the rank of T to be the dimension of the rank of the range, and the nullity of T to be the dimension of the kernel of T. Now, why are these things subspaces? It's not difficult at all to show. I'm going to do only one of them. I'll focus on the kernel because, frankly, the proof is easier. If you wish to see the other one, you go ahead and look in the book. It's very easy to follow. It's exactly the same proof, actually, I did way back when I was looking at column space and null space. It's the exact same thing. So just to show you why, really quickly, let's suppose that you have two vectors. Let's say V and U that are in the kernel, of T. If that's true, then T of U is equal to T of V, and that's the zero vector. All I have to do is show you that if I take these two vectors and add them, you're back in the kernel. So, but notice though that T of U plus V would be T of U plus T of V, and that's the zero vector. And for any scalar, C, T of C times U would then be C times T of U, and that's just the zero vector again, because it's C times zero vector. So then this set, the kernel, is closed under vector addition and scalar multiplication. It's a subspace of V. You can do basically the same kind of argument for W, and I'll again just leave the proof for you. It's not difficult at all. But you do need to have a picture in mind because it helps visualize what's going on. So you have a vector space V. It's a collection of vectors. Some of those vectors are the kernel. The kernel is its own vector space. It's a subspace inside of a vector space. But the transformation maps all the vectors in V into W. Well, but in W, the image of V is the range of V, but the range is a subspace. So I'm representing that range as a line because it's something similar to you're used to. It's a line that goes to the origin. But all the vectors in the kernel, all of them get mapped to the origin. So there's a sense of collapsing. If the kernel is not zero, there's a sense of collapsing the space V to squish it, to make it fit inside the vector space W. Notice that this pretty much implies instantly that if W is finite dimensional, then the range of T is finite dimensional and is in less dimension. So the rank of T has got to be less than or equal to the dimension of W. And we've heard that before with matrix transformations, remember? It just took us a lot longer to do. Cool. Let's just go try it a couple times. So every single transformation then has a range and has a kernel, and therefore has a nullity and a rank. So you've already seen 3 or 4 examples from before of transformations. And when I computed their rank, I computed their range and their kernel. I'm just going to go back now and show you what their nullity and rank would be. So if you have an m by n matrix and you look at T sub A, the corresponding matrix transformation that goes from Rn to Rm defined by matrix multiplication. So then T of X would then be A times X. You already know that the kernel of T was the null space of A. So then the nullity of the transformation is actually the same as the nullity of that matrix. They're the same thing. And since the range of the transformation is the column space of A, Therefore, the rank of the transformation is the same as the rank of the matrix. So it's really nice. You have this nice correspondence between these ideas. If you look at the derivative transformation going from P3 to P2, I already computed the range for you, and I already computed the kernel of it. So then because of that, since I know the range, I can tell you the rank right away. So the rank then of D is just the dimension of the range, which is the dimension of P2, which is 3, right? It has 3 vectors in spaces, 1, x, x squared. Then I need to know the nullity. So the nullity of this operator is the dimension of its kernel. But it's spanned by the number 1, right? It's just one real number. So the nullity here is just 1. Notice that the sum of these is 4, and that happens to be the dimension of P3, where you came from. Let's try it again. So if you look at if you want to find the kernel and the range, and therefore get the nullity and the rank of this transformation, we already know from before what the range is. We know from before what the kernel is. So because of that, I can instantly tell you what the rank is. It's literally just the number of vectors needed to go and be a basis for the range, which here is just 1. And the nullity of this transformation is literally just the number of vectors that are needed to make a basis for the kernel, which here is just 3. Notice though, if you add these numbers, you get 4, and that happens to be the dimension of the original domain. Cool. I think then you're convinced, hopefully by example, that if you have a linear transformation going from 2 vector spaces, they could be finite dimensional or not. They could be finite dimensional or not. Then the rank of T plus the nullity of T is actually the dimension of the domain. So that's incredibly useful. If this is actually always true, it's incredibly useful, because that means we don't have to worry about computing both the rank and the nullity. You just find one of them. It would automatically usually find the other one for us. So for example, here, let's find the nullity and rank of this guy. I don't want to. We already did though. I already computed for you what the corresponding kernel was. You remember the kernel of this transformation was the span of just one vector, which was 1 minus 2x. So the nullity would then have to be 1. But then since this space here is finite dimensional, that means that the rank of T would have to be the dimension of P1 minus the nullity of T. But that is then 2 minus 1, and that'd be 1. Neat, right? We don't even have to find out what the range is, but I can find out what its dimension of its space is. That's kind of nice. So let's just practice that a couple more times to make sure you understand. Notice that this has another very interesting result, and that is if the dimension of V is finite, then the rank of T is also less than it. So the rank of T is also less than or equal to the dimension of the domain. So the rank being the range, the dimension of the range, is less in dimension than the domain space and the codomain space. It's neat. And that's the exact same result we had way back when with matrices, by the way. Same thing. It's just with linear transformations now. So as our last quick example, let's consider just a generic linear transformation. I'm not going to tell you what it looks like. I'm not going to tell you what it is. It's going from M22 to P2. What could the rank of T equal? Well, so then remember that the rank of T plus the nullity of T has got to be the dimension of the domain. So that's the dimension of M22. That's 4. So the rank is a non-negative integer. So the rank could only be 0, 1, 2, 3, or 4. But it also must be less than the dimension of the codomain space. So the dimension of P2 is only 3. So then the rank of this thing, this transformation, could be 0, 1, 2, or 3. That's it. Now you know that. Since we know the rank potentially, we didn't know what the nullity could be. So the nullity of T is going to be 1, 2, 3, or 4. Because they have to add, the numbers have to add to be 4. That's it. So the nullity is at least 1. So the kernel is a non-trivial subspace. It has more than just a 0 vector in it. I don't know what it is, but I know therefore this transformation, whatever it does some kind of collapsing. I believe that's enough for that video.